Okay, let's just dive right into this explainer. I want to speak directly to the developers and project managers in the room today. Look, we're here to ensure your offshore energy investments remain commercially viable and honestly, durable over the long haul. Tidal Energy is at a real inflection point right now, and the decisions you're making today about station-keeping systems, well, they're going to dictate whether your project actually thrives or just completely drowns in maintenance costs. So it really boils down to this fundamental question. How do we guarantee a 25-year lifespan in some of the absolute harshest marine environments on Earth? It's a massive deal because replacing hardware offshore absolutely wrecks your return on investment. If you're constantly having to send out maintenance vessels to fix fatigue damage, your levelized cost of energy is simply never going to compete with traditional sources. To get to true commercial competitiveness, we've got to make a major shift. We have to transition away from these rigid structures that basically just fight the ocean and move toward flexible systems that actually work with it. The old standard relies on brute force, whereas this new standard, it relies on dynamic physics. Here is our executive briefing itinerary for today. 1. The commercial challenge. 2. Fixed versus flexible systems. 3. The anatomy of tensioned systems. 4. Buoys as load dampers. And finally, 5. Proving system durability. All right, moving into section 1, the commercial challenge. Look, we already know the underlying tech works, right? The first large-scale facilities like the MeyGen project have successfully pumped gigawatt hours to the grid. Viability is proven. But here's the catch. If you're relying on drilled monopiles, pin pile tripods, or these massive gravity bases, you are eating huge installation costs right out of the gate. And even worse, by rigidly locking your turbine to the seabed, you're forcing your equipment to take the brunt of brutal, unsteady marine loads. That crucial 10 to 25-year fatigue life is severely threatened when your structure has to absorb every single ounce of wave and current force head-on. Which brings us to section 2, fixed versus flexible systems. The real game changer here is utilizing a neutrally buoyant turbine on a flexible mooring system. So instead of bolting a turbine to a giant steel pipe drilled into the rock, the turbine is actually suspended right there in the water column. It's neutrally buoyant, meaning it doesn't sink and it doesn't float to the surface. This completely rewrites the physics of how your hardware interacts with the current. You're shifting the entire paradigm from rigid resistance to a dynamic response. Let's look at section 3, anatomy of tensioned systems. What's really striking here is just how simple the design is. You've got the seabed anchor, a tether line, the neutrally buoyant turbine itself, and this is key, a fully submersed buoy up top. These mooring lines are continuously in tension during operation, which means the whole thing acts as a single dynamic unit rather than a stiff, unyielding pillar. Because you've got that buoy applying upward tension and the tether pulling downward, the entire setup acts like what physicists call an inverted flail pendulum. It literally responds to the sea state. When a thrust load hits the turbine or a wave hits the buoy, the system can actually yield a bit. It sways. This allows the whole setup to dynamically absorb wave and current forces instead of just rigidly resisting them and racking up structural fatigue. Moving into section 4, submerged buoys as load dampers. Now that buoy isn't just there to keep the string tight, it's actually an active damper. By oscillating up there in the waves, it modifies the relative velocity between the turbine and the water inflow. As the buoy moves with the wave excitation, it essentially pulls the turbine in ways that perfectly offset the heaviest impacts of the current. It's acting like a massive shock absorber for your expensive rotor blades. Finally, section 5, proving system durability. You need the hard data, right? This model simulated a 1 megawatt turbine across different wave and current setups, and what we're looking at is the standard deviation of thrust. For the engineers listening, you know standard deviation of thrust is exactly what causes long-term fatigue failure, those violent fluctuations in force. Well, as you can see in both steep and swell sea states, that standard deviation just plummets when you use the tensioned mooring system instead of a rigid support. Let's break those numbers down a bit. In steep wave environments, what we'd call sea state 1, the tensioned mooring system drops the peak loading down to just 41.7% of what a rigid structure would take. That is a massive, absolutely crucial reduction in the physical stress your turbine blades are dealing with, day in and day out. But it gets even better. In swell sea states, those longer rolling waves, when you factor in the wave excitation acting on the buoy, the peak load deviation drops to an astonishing 13.9% of the rigid baseline. 13.9%. The buoy perfectly synchronizes with those long wave periods, creating an incredibly favorable load reduction. If we look at this waveform from the swell simulation, it paints a very clear picture. The green line, which is our wave-excited buoy system, totally smooths out those violent, towering thrust peaks you see in the blue line, which represents the rigid support. That blue line, that's what destroys gearboxes and shears blades. The green line is what actually gives you a 25-year operational life. Now, as your advisor, I do have to give you the full picture. There is a caveat. During extremely harsh winter storms, think the absolute worst the North Sea can throw at you, the system does face a unique challenge. The displacement of the buoy and the turbine can get so severe, shifting deeply into the wave troughs, that the velocities on the blade elements change drastically. This causes a larger angle of attack, creating massive drag and negative torque. Basically, the turbine stalls. So for those extreme events, you're going to need to manage blade pitch actively, maybe look at different airfoil profiles, or just plan for safe automated shutdowns to protect the rotor. All right, to wrap up today's strategic briefing, moving to a flexible, neutrally buoyant system lowers your upfront foundation and installation costs right away. And by bringing in a submerged buoy, you get this incredibly powerful load damper that mathematically extends the fatigue life of your turbines by slashing peak thrust. You just need to make sure your engineering teams optimize for those extreme winter stall conditions. At the end of the day, the ocean always wins against a rigid wall. It will relentlessly test every single weld and bolt until it finds a failure point. So as you're planning out capital allocation for the next decade of offshore energy, you really have to ask yourself, is your next investment going to fight the current or flow with it?